Since civilization's dawn, humanity has stared into darkness, mesmerized by our celestial companions' unchanging gaze. Night after night, the same luminous disk reveals identical features: familiar craters, shadowy valleys, brilliant peaks that have sparked legends across cultures. Yet concealed behind this eternal face exists a completely foreign landscape so dramatically different, it defies imagination. 65 years ago, mankind shattered millennia of ignorance when Soviet technology finally unveiled what had remained Earth's greatest secret. The revelation was staggering. Me as our moon possesses two entirely separate worlds. While one hemisphere bathes us in familiar silver light, the other harbors terrain so alien, so violently scarred, that discovering it felt like finding another planet hiding in plain sight. Tonight's expedition ventures into this forbidden realm where physics whispers ancient secrets about cosmic birth, where catastrophic collisions carved wounds spanning entire continents, where recent discoveries are demolishing everything science believed about our nearest neighbor. The hidden hemisphere challenges every assumption, revealing mysteries that could reshape our understanding of planetary formation itself. Before we plunge into these lunar depths together, drop a comment revealing your location and what cosmic enigmas fascinate you most. Your engagement fuels these explorations, helping fellow space enthusiasts discover these incredible journeys we're sharing. Each like and subscription builds our community of cosmic curiosity. The foundation of this mystery rests upon gravitational choreography, perfected across billions of years. Our lunar companion performs synchronous rotation missions and a celestial waltz, where rotational period perfectly matches orbital duration. This cosmic timing locks one hemisphere toward Earth, while condemning the opposite side to eternal darkness from human perspective. Ancient civilizations crafted elaborate mythologies around lunar mysteries, yet none envisioned an entire world concealed beyond their observations. Greeks named it Selene, Romans called it lunar, but every culture witnessed identical patterns, identical shadows, identical bright regions forming humanity's collective lunar legacy. October 7th, 1959 marked humanity's first forbidden glimpse, when Luna 3's primitive cameras captured revolutionary photographs of previously invisible terrain. Despite fuzzy imagery limited by 1950s technology, these pictures revealed something profoundly disturbing. The concealed hemisphere bore no resemblance to familiar near-side features. Where Earth-facing regions displayed vast dark plains that ancient astronomers mistook for oceans, the hidden territory showed landscapes dominated by brilliant, densely cratered highlands. Smooth basaltic maria creating the man-in-the-moon pattern were virtually absent. Instead, this mysterious hemisphere presented terrain appearing more ancient, more battered, more extraterrestrial than anyone had dared contemplate. This initial revelation sparked questions, consuming lunar scientists for decades. What cosmic forces created such dramatic hemispheric differences? Why did two halves of the same celestial body appear sculpted by completely different processes? What secrets might this alien landscape harbor about lunar formation and early solar system violence? Those grainy Luna 3 images established one undeniable truth. Our moon was infinitely more complex than previously imagined. The hidden hemisphere wasn't simply a mirror reflection of known territory. It represented an entirely different world, shaped by distinct geological processes, and preserving unique stories about the cosmic bombardment that forged our solar system's architecture. Advancing space exploration through subsequent decades brought increasingly sophisticated observations of these stark hemispheric contrasts. Apollo missions focused on near-side regions for safety and communication advantages, provided humanity's first detailed understanding of lunar geology. However, the far side remained largely enigmatic, accessible only to robotic explorers and orbital reconnaissance using progressively advanced instruments. These investigations painted a portrait of asymmetry so extreme it challenged fundamental planetary formation theories. The near side, with abundant volcanic plains, told stories of a geologically active moon where massive lava flows filled ancient impact basins, creating dark features visible to naked-eye Earth observers. Conversely, the far side revealed completely different narratives, a world where volcanic activity remained severely limited and ancient impact craters stayed largely unfilled and unmodified. The concealed hemisphere's crust proves significantly thicker than near-side regions, sometimes exceeding differences of 50 kilometers. This thickness variation carried profound implications for lunar geological evolution, affecting everything from magma's surface accessibility to ancient impact structure preservation. Where near-side's thinner crust permitted molten rock eruptions creating vast lava plains, the far side's thick crustal barrier largely prevented such volcanic resurfacing. Perhaps the most captivating feature of this hidden realm is a structure so colossal and ancient it ranks among the solar system's most significant geological formations. The South Pole-Aitken Basin, spanning approximately 2,500 kilometers across the Moon's southern hemisphere, represents one of the largest and oldest impact craters ever documented. This enormous lunar scar, carved by asteroid collision roughly 4.3 billion years ago, offers unprecedented insights into the Moon's deep interior and violent processes that shaped early solar system development. The basin's formation involved almost incomprehensible violence. An asteroid possibly hundreds of kilometers in diameter struck with such tremendous force that excavated material potentially reached the lunar mantle itself. The impact's incredible power led some scientists to theorize it may have caused lunar axial shifting, potentially contributing to the hemispheric differences we observe today. Within this ancient wound lies one of modern lunar science's most bewildering puzzles. Deep beneath the basin's floor, gravity measurements from NASA's Grail mission detected a massive anomaly, the dense material concentration weighing more than 5 times Hawaii's Big Island mass. This mysterious buried mass, located over 300 kilometers below surface, has ignited intense scientific debate regarding its nature and origin. The prevailing hypothesis suggests this anomaly might represent remnants of the basin-creating asteroid, its iron-nickel core somehow embedded within the Moon's upper mantle during the cataclysmic impact. If accurate, this buried metallic mass would preserve a piece of early solar system history, a relic from when planets and moons endured constant massive asteroid bombardment. However, the South Pole-Aitken Basin conceals secrets extending far beyond its mysterious buried mass, promising revelations that could revolutionize our understanding of lunar and planetary science forever. The catastrophic collision that birthed this colossal basin unleashed such devastating force that it potentially exposed lunar interior materials never before accessible on the surface. These extraordinary substances, excavated from depths typically buried beneath kilometers of crustal rock, provide scientists unprecedented opportunities to examine the Moon's internal composition without requiring expensive deep drilling operations. Revolutionary analysis of specimens retrieved by China's Chang'e 6 mission from within this ancient crater has unveiled volcanic rocks dating back 2.8 billion years, substantially younger than most near-side samples. This groundbreaking discovery indicates the concealed hemisphere maintained volcanic activity far longer than scientific models predicted, fundamentally challenging existing theories about lunar thermal evolution, while raising profound questions about the mechanisms driving this extended geological dynamism. The existence of these comparatively recent volcanic formations becomes particularly enigmatic when examined alongside the far side's characteristically thick crust and sparse volcanic plains. How did molten material successfully penetrate surface layers in this region when similar processes were largely blocked elsewhere across the hidden hemisphere? The solution may reside in extraordinary conditions generated by the South Pole-Aitken impact itself, which potentially fractured crustal barriers and established magma pathways persisting across billions of years. Among the most revolutionary findings from Chang'e 6 specimens was detecting creep basalt's MERS rocks enriched with potassium, rare earth elements, and phosphorus. These materials were previously believed concentrated primarily on the Moon's near side, where they helped explain abundant volcanic activity patterns. Discovering creep basalts on the concealed hemisphere completely overturns this understanding, suggesting lunar compositional asymmetry may originate from entirely different sources than previously theorized. Creep materials carry special significance because they contain heat-producing radioactive elements capable of sustaining volcanic activity long after a planetary body's initial formation energy has dissipated. Their presence across the hidden terrain raises fascinating questions about how lunar thermal evolution may have varied between hemispheres and why volcanic processes persisted longer in certain regions while ceasing in others. These discoveries' implications stretch far beyond lunar science boundaries. Our moon functions as a preserved archive of early solar system history, the world where ancient surfaces and impact structures remain largely unaltered by weathering and geological processes that have obliterated similar features on Earth. Through studying the concealed hemisphere, scientists gain invaluable insights into cosmic bombardment that shaped all inner planets during our solar system's turbulent youth. The extreme antiquity and preservation of far-side impact structures provide an unparalleled laboratory for understanding collision processes and their effects on planetary bodies. Unlike Earth, where erosion and plate tectonics have erased most evidence of primordial impacts, the Moon's hidden face preserves detailed records of projectiles that pummeled the inner solar system billions of years ago. These ancient impact formations also offer crucial clues about asteroid distribution and composition throughout the early solar system. By examining chemistry and mineralogy of impact, melt rocks and crater structures, scientists can deduce properties of colliding bodies while gaining insights into processes that shaped planetary formation across our cosmic neighborhood. However, the scientific significance of the lunar far side extends beyond its role as an early solar system museum. The distinctive properties making it so dramatically different from the near side also render it an optimal location for specific types of scientific observations and future exploration endeavors. The far side's position, permanently shielded from Earth's radio interference, creates one of the quietest electromagnetic environments within the inner solar system. This natural radio silence makes it supremely suitable for radio astronomy, particularly observations of the early universe at frequencies completely blocked by Earth's ionosphere. Radio telescopes operating from the lunar far side could potentially detect signals from the cosmic dark ages, the period when initial stars and galaxies were forming but hadn't yet begun emitting visible light. These observations could revolutionize our understanding of cosmic evolution, providing insights into processes occurring when the universe was merely a few 100 million years old. NASA and international space agencies are already developing plans to exploit this unique environment. The proposed Lunar Crater Radio Telescope would utilize robotic systems to deploy a kilometer-diameter wire mesh antenna within a suitable far-side crater, creating the largest filled-aperture radio telescope in our solar system. Such an instrument could observe radio frequencies completely inaccessible to Earth-based telescopes. The concealed hemisphere also offers unique advantages for additional types of astronomical observations. The absence of atmospheric interference combined with lunar surface stability and minimal seismic activity could provide ideal conditions for optical and infrared telescopes. The lunar environment's lack of weather, wind, and atmospheric disturbances would enable observations of unprecedented clarity and stability. Beyond scientific value, the far side's unique characteristics make it an intriguing location for future lunar bases and resource extraction activities. Permanently shadowed regions near lunar poles, many located on or adjacent to the far side, contain some of the coldest environments in our solar system. These regions function as natural cold traps, preserving volatile materials like water ice that would rapidly sublimate in sunlit areas. Recent discoveries have confirmed significant water ice deposits in these permanently shadowed regions, with some craters estimated to contain millions of tons of accessible frozen water. This resource could prove crucial for future lunar exploration, providing not only drinking water for astronauts but also raw materials for rocket fuel production through water splitting into hydrogen and oxygen components. Extraction and utilization of lunar water ice could transform space exploration by establishing a refueling station for missions to Mars and outer solar system destinations. Rather than transporting all necessary propellant from Earth's deep gravity well, spacecraft could refuel at lunar facilities, dramatically reducing costs and complexity of deep space missions. As we advance our exploration of the Moon's hidden hemisphere, each discovery adds complexity to an increasingly fascinating portrait. The far side isn't simply the dark side of popular imagination, but a world of ancient impacts, mysterious anomalies, and unique opportunities continuing to challenge our understanding of planetary formation and evolution. The story of the concealed hemisphere continues evolving, with each mission and technological advancement revealing fresh insights into this alien yet familiar world. From massive buried anomalies beneath ancient impact basins to surprisingly young volcanic rocks indicating extended geological activity, the hidden hemisphere continues surprising and intriguing scientists globally. Differences between lunar hemispheres penetrate deeper than surface geology, extending into realms challenging our most fundamental planetary science understanding. When scientists analyzed data from increasingly sophisticated lunar missions, they discovered that near-side-far-side asymmetry represents one of the most extreme hemispheric dichotomy examples found anywhere in our solar system. Chemical composition of far-side rocks tells stories of processes so different from near-side experiences, they might describe separate worlds entirely. Where Apollo specimens from near-side regions revealed abundant titanium, iron, and heavy elements, typical of basaltic volcanism, far-side materials showed markedly different signatures enriched in aluminum and calcium, characteristic of ancient highland materials forming the Moon's primordial crust. This compositional dichotomy extends beyond simple surface variations into the Moon's deep interior. Seismic studies have revealed structural asymmetries mirroring surface differences, with the concealed hemisphere's crustal thickness variations creating distinctive seismic signatures that helped researchers map lunar internal architecture with unprecedented precision. These structural disparities carry profound implications for understanding lunar formation and evolution processes. The predominant theory proposes our Moon originated from a Mars-sized object called Theia that collided with primordial Earth approximately 4.5 billion years ago. This catastrophic impact ejected enormous quantities of material into Earth orbit, which gradually coalesced, forming our celestial companion. Yet if the Moon formed from such devastating collision, why did it develop such extreme hemispheric asymmetry? The explanation may reside in complex planetary accretion physics and unique circumstances during lunar early evolution. Computer simulations indicate our Moon may have initially formed much closer to Earth than its current position, experiencing intense tidal heating that maintained much of its interior molten for extended periods. During this primordial phase, lunar rotation was likely substantially faster than today, with a highly elliptical orbit. The combination of tidal forces, rotational dynamics, and continuous bombardment from asteroids and comets may have created conditions preferentially concentrating specific materials on one hemisphere, while depleting them on the opposite side. The South Pole-aitken impact may represent the defining event that permanently established these hemispheric differences. This massive collision not only created our solar system's largest impact basin, but potentially triggered hemisphere-scale convection within the lunar interior. Computer models suggest the impact's tremendous energy could have initiated convection patterns transporting heat-producing radioactive elements toward the near side, establishing conditions for sustained volcanic activity there, while leaving the concealed hemisphere relatively depleted. This radioactive element redistribution would explain numerous observed hemispheric differences. Uranium, thorium, and potassium concentration on the near side would have provided necessary heat for driving volcanic activity across billions of years, creating extensive lava plains visible today. Meanwhile, the far side, depleted of these heat sources, would have cooled more rapidly while retaining its ancient, heavily cratered appearance. Recent orbital missions have provided increasingly detailed elemental distribution maps, confirming radioactive elements are indeed concentrated on the near side. The Lunar Prospector's gamma-ray spectrometer created comprehensive charts showing uranium, thorium, and potassium distribution across the lunar surface, revealing patterns strongly supporting hemispheric redistribution hypotheses. However, the narrative becomes increasingly complex considering late-stage volcanic activity on the concealed hemisphere. Discovering 2.8 billion-year-old basalts within the South Pole-Aitken basin challenges simple hemispheric evolution models. How could volcanic activity persist on the far side for such extended periods if truly depleted of heat-producing elements? The solution may lie in unique conditions created by the basin-forming impact itself. This massive collision not only excavated enormous material quantities, but also generated deep crustal fractures serving as magma transport conduits. Even minimal radioactive heating within lunar interior could drive volcanism if efficient pathways existed for molten material reaching the surface. The discovery of creep materials in far-side specimens adds another puzzle layer. These potassium, rare earth element, and phosphorus-rich rocks were believed primarily near-side phenomena, concentrated in regions like Oceanus Procellarum, where they contributed to sustained volcanic activity. Finding similar materials on the concealed hemisphere suggests lunar early differentiation was more complex than previously understood. Creep represents final products of lunar magma ocean crystallization, remnants of a global molten layer existing during the Moon's earliest history. As this magma ocean slowly cooled and crystallized, dense minerals sank toward the interior while lighter materials floated surfaceward. Creep represents the final liquid crystallizing, enriched in elements that didn't fit easily into common lunar mineral crystal structures. Creep presence on both hemispheres suggests this late-stage differentiation product was initially distributed more evenly than current surface concentrations indicate. Subsequent processes, possibly including the South Pole-aitken impact and its aftermath, may have redistributed these materials, creating asymmetric patterns observed today. Understanding these processes proves crucial for interpreting the Moon's role as an early solar system history recorder. The lunar surface preserves evidence of the late heavy bombardment, a period approximately 4 billion years ago when the inner solar system experienced intense asteroid and comet impact spikes. This bombardment may have been triggered by outer solar system gravitational instabilities sending icy bodies streaming sunward. The far side's heavily cratered terrain provides particularly well-preserved bombardment records. Unlike the near side, where volcanic activity obscured many impact structures, the concealed hemisphere retains craters from throughout lunar history. These ancient scars serve as windows into projectile populations that battered inner planets during early evolution. By studying far-side crater sizes, distributions, spatial patterns, and ages, scientists can reconstruct impacting body flux over time and understand how this bombardment shaped planetary surfaces throughout our solar system. Insights gained from lunar crater studies extend far beyond our solar system, informing our understanding of planet formation and evolution around other stars. Ancient surface preservation on the far side also makes it ideal for studying space weathering effects. Gradual surface material alteration by solar wind particles, cosmic rays, and micrometeorite impacts. Over billions of years, these processes modify surface material optical and chemical properties, creating characteristic appearances of airless planetary bodies. Understanding space weathering proves crucial for interpreting remote sensing observations of asteroids, comets, and other airless bodies throughout our solar system. The Moon serves as a natural laboratory where scientists can study these processes comprehensively and develop models applicable to other worlds. The concealed hemisphere's unique environment offers unprecedented astronomical observation opportunities impossible from Earth. The Moon's position between Earth and distant cosmic sources creates natural radio shadows blocking terrestrial interference across wide frequency ranges. This radio-quiet environment proves particularly valuable for low-frequency radio astronomy, where Earth's ionosphere creates impenetrable barriers to ground-based observations. Radio waves at frequencies below approximately 30 MHz carry information about fundamental universe processes. These low-frequency signals can reveal cosmic dark age details, the period between universal initial cooling and first star formation. During this era, neutral hydrogen-filled space, observable only through its characteristic 21 cm emission line, redshifted to much longer wavelengths by cosmic expansion. A radio telescope operating from the lunar far side could potentially detect these ancient signals, providing direct observations of cosmic structure formation during the universe's initial few hundred million years. Such observations would complement and extend space-based mission capabilities, like the James Webb Space Telescope, which can observe first galaxies in infrared light, but cannot peer back to pre-stellar eras. Technical challenges of deploying and operating far-side radio telescopes are substantial yet surmountable. The proposed Lunar Crater Radio Telescope would require sophisticated robotic systems capable of deploying wire mesh antenna elements across kilometer-scale distances within suitable impact craters. Natural bowl shapes of large craters provide ideal geometries for creating spherical reflectors focusing radio waves onto sensitive receivers. Such facilities would need autonomous operation during lunar nights, when solar radio interference is minimized and most sensitive observations can be conducted. Lunar nights last approximately 14 Earth days, providing extended stable observing periods unavailable from any Earth-based facility. Far-side radio astronomy's scientific potential extends beyond cosmological observations. Low-frequency radio waves can penetrate deeply into planetary interiors, making them valuable for studying subsurface structures of planets and moons throughout our solar system. Water ice within permanently shadowed regions represents far more than merely convenient resources for future lunar inhabitants. The capability to extract and process lunar water could revolutionize space exploration by providing locally manufactured rocket fuel for missions to Mars and beyond. Chemical splitting of water into hydrogen and oxygen generates high-performance propellants, enabling refueling operations throughout the inner solar system. The economic ramifications of lunar water extraction are absolutely staggering. Current launch costs make transporting large quantities of water or fuel from Earth's surface to deep space prohibitively expensive. A lunar refueling infrastructure could reduce mass requirements for interplanetary missions by orders of magnitude, opening possibilities for sustained exploration of Mars, the asteroid belt, and outer solar system destinations. However, accessing these resources demands overcoming substantial technical challenges. Permanently shadowed regions experience some of our solar system's coldest temperatures, approaching absolute zero in certain locations. Operating robotic equipment under these extreme conditions while extracting and processing water ice will push current technology boundaries to their limits. The preservation of water ice in these regions across billions of years reveals something profound about lunar thermal history and volatile sources throughout the inner solar system. Some of this ice may have originated from cometary impacts during the late heavy bombardment, preserving ancient water from outer solar system regions within these natural cold traps. Isotopic analysis of lunar ice could provide crucial insights into Earth's water sources and delivery mechanisms that transported volatiles to inner planets. Understanding these processes proves essential for assessing rocky exoplanet habitability potential and the likelihood of discovering water-rich worlds around other stars. The concealed hemisphere continues surprising researchers with discoveries challenging our understanding of lunar evolution and planetary science more broadly. Each mission reveals additional complexity in what was once considered a geologically simple world. From massive buried anomalies beneath impact basins to unexpected preservation of ancient magnetic signatures, the hidden hemisphere keeps rewriting scientific textbooks. Recent magnetic field measurement analysis has revealed that our moon once possessed a global magnetic field comparable in strength to Earth's current field. This ancient magnetosphere left its signature embedded in lunar rocks, creating a magnetic field evolution record spanning billions of years. The far side preserves some of the strongest and most ancient magnetic signatures, suggesting it may hold crucial clues about lunar magnetic history. Understanding how and why the moon's magnetic field evolved provides insights into thermal and dynamic evolution of its interior. Planetary magnetic field generation requires convection in electrically conducting fluids, typically molten metal cores. The moon's small size should have allowed its core to cool and solidify relatively quickly, yet evidence suggests magnetic field generation persisted much longer than simple cooling models would predict. Strong magnetic signature preservation on the far side may relate to the hemisphere's thicker crust and different thermal history. These magnetic anomalies could represent fossil records of impact-induced magnetic field generation or evidence for more complex core dynamics than previously understood. As we continue peeling back lunar mystery layers, the far side emerges not merely as a complement to the familiar near side, but as a world unto itself with its unique formation, evolution, and preservation story. Each crater, mineral grain, and magnetic anomaly adds another piece to the vast puzzle of how worlds form and change across cosmic time. The hidden hemisphere has transformed from a curiosity glimpsed in grainy photographs to a crucial piece of our solar system story, one continuing to yield surprises and challenge our most fundamental planetary science assumptions. As we prepare for lunar exploration's next chapter with new missions, advanced instruments, and eventually human explorers returning to the moon, the far side stands ready to reveal even more carefully guarded secrets. The technological marvels enabling far side studies represent some of humanity's most sophisticated space exploration achievements. When NASA's Lunar Reconnaissance Orbiter began systematic moon surveys in 2009, It carried instruments capable of peering through lunar surface and mapping subsurface structures with unprecedented precision. The spacecraft's laser altimeter could measure surface elevations within centimeters, while its cameras captured images detailed enough to reveal features smaller than dining room tables. However, perhaps the most revolutionary tool for understanding the far side has been the gravity recovery and interior laboratory mission known as GRAIL. This ambitious project employed two spacecraft flying in precise formation around the Moon, constantly measuring tiny gravitational field variations as they orbited. When one spacecraft passed over higher density regions, it would experience slight acceleration detectable by monitoring radio signals passing between both vehicles. GRAIL mission discoveries beneath the South Pole-aitken basin rank among planetary science's most startling revelations. Deep within lunar interior, buried beneath kilometers of crustal rock, lies a mass so dense and extensive it defies easy explanation. This subsurface anomaly stretches across hundreds of kilometers and penetrates deep into lunar mantle, representing material concentration unlike anything found elsewhere in our solar system. The leading explanation for this buried treasure suggests we're observing fossilized remains of the asteroid that created the basin itself. When that ancient impactor struck the Moon with unimaginable violence, its metallic core may have become embedded in lunar interior like a cosmic bullet frozen in time. If this interpretation proves correct, we have preserved within our Moon a pristine sample of early solar system materials, a piece of the primordial disk from which all planets formed. The implications extend far beyond lunar science boundaries. This buried metallic mass could represent our most accessible sample of early solar system materials, preserving isotopic signatures and chemical compositions erased elsewhere by billions of years of geological processing. Future missions might attempt reaching these materials through deep drilling operations, potentially revolutionizing our understanding of planetary formation throughout the galaxy. The mystery deepens when considering the basin's role in shaping lunar subsequent evolution. Computer simulations suggest the South Pole-aitken impact may have triggered convection patterns in lunar interior, persisting for hundreds of millions of years. These convection cells could have transported heat-producing elements from the impact site toward other lunar regions, creating chemical asymmetries we observe today. This process might explain one of the Moon's most perplexing characteristics: the concentration of radioactive elements in a region called the Procellarum creep terrain on the near side. This vast province, visible as dark areas forming the man in the moon pattern, contains elevated uranium, thorium and other heat-producing element levels that sustained volcanic activity long after lunar initial formation heat had dissipated. The discovery that similar materials exist on the far side, albeit in different concentrations and distributions, suggests lunar early differentiation was far more complex than previously imagined. Rather than simple layered structure formed by straightforward crystallization of a global magma ocean, we're witnessing evidence for dynamic processes that redistributed materials across hemispheres through mechanisms still being unraveled. These discoveries have profound implications for understanding how planetary bodies differentiate and evolve. The Moon serves as a natural laboratory where scientists can study processes that occurred during the early solar system but have been obscured on Earth by billions of years of geological activity. The preservation of ancient impact structures on the far side provides unique opportunities to study collision processes that shaped all terrestrial planets. Unlike Earth, where erosion and plate tectonics have erased most evidence of early bombardment, the lunar surface maintains detailed records of projectiles that battered inner solar system worlds during their formation. Each crater tells a story about the size, velocity, and composition of impacting bodies, allowing scientists to reconstruct the population of asteroids and comets that existed during the solar system's violent youth. This information proves crucial for understanding how planetary formation processes operated, not only in our solar system but potentially around other stars as well. The far side's unique preservation of ancient surfaces also makes it invaluable for studying space weathering processes, the gradual alteration of surface materials by solar wind particles, cosmic rays, and micrometeorite bombardment. These processes modify optical and chemical properties of airless body surfaces over geological timescales. Understanding space weathering proves essential for interpreting remote sensing observations of asteroids, comets, and other airless bodies throughout our solar system. The Moon provides a controlled environment where scientists can study these processes in detail and develop models applicable to other worlds. Mechanisms that transported substances across vast hemispheric distances through complex planetary scale redistribution events. Fresh examination of Chang'e and Emiso-6 specimens has unveiled additional layers of complexity within this narrative. The igneous materials retrieved from the concealed hemisphere exhibit isotopic fingerprints indicating formation from mantle sources, severely stripped of particular elements. This extremely depleted characteristic suggests the hidden hemisphere's mantle experienced extensive processing, potentially through numerous partial melting episodes that removed easily extractable components. The chronology of this depletion process remains enigmatic, yet may connect to colossal collisions that sculpted lunar early history. Every massive impact would have generated tremendous thermal energy while potentially triggering widespread interior melting. Cumulative effects from multiple large-scale collisions could have established the intricate chemical stratification observed in contemporary lunar specimens. Comprehending these mechanisms proves vital for interpreting our Moon's function as testimony to the primordial solar system's turbulent past. The lunar terrain maintains documentation of the late heavy bombardment period, while chemical fingerprints locked within rocky materials narrate even more comprehensive stories regarding projectiles that struck during this pivotal era. The concealed hemisphere's crater assemblage provides exceptional perspectives into this ancient bombardment phase. While near-side crater documentation has been partially concealed by volcanic processes, the hidden territory preserves collision structures spanning complete lunar bombardment chronology. These formations range from enormous primordial basins created during our solar system's earliest phases to minute recent craters generated by contemporary impacts. Statistical examination of crater dimension distributions exposes patterns constraining early solar system dynamics models. Size-frequency correlations of far-side craters align with theoretical projections for asteroid and comet populations present during various solar system evolutionary periods. This correspondence supplies robust validation for our comprehension of how planetary bombardment frequencies have transformed across time. Nevertheless, the crater documentation also unveils surprises challenging conventional understanding about collision mechanisms. Several far-side impact basins demonstrate evidence for multiple collision events occurring within relatively brief temporal intervals, indicating early bombardment may have been more temporally clustered than previously assumed. These chronological groupings might reflect gravitational disturbances in outer solar system regions that periodically dispatched projectile swarms streaming toward interplanetary bodies. Preservation of these ancient collision structures on the hidden hemisphere also establishes natural laboratories for investigating impact physics under conditions no longer existing elsewhere within our solar system. The Moon's atmospheric absence and geological inactivity means collision craters remain largely unaltered across billions of years, maintaining details about shock propagation, melt production, and crater modification that have been eliminated from more geologically dynamic worlds. Sophisticated computer modeling now permits researchers to simulate these ancient impacts with extraordinary precision, incorporating everything from impactor velocity and composition to target thermal conditions and structural characteristics. When these models undergo comparison with actual lunar crater observations, they expose insights about collision processes applicable throughout our solar system and beyond. The hidden hemisphere's function as a cosmic archive extends beyond impact craters to maintain evidence of other fundamental mechanisms that shaped early solar system development. Ancient highland materials dominating far-side landscapes represent some of our planetary system's oldest solid substances, crystallized from the global magma ocean enveloping the newly formed Moon. These primordial materials contain isotopic fingerprints constraining lunar formation and early evolutionary models, ratios of different oxygen isotopes within lunar highland specimens, for instance, supply crucial examinations of the giant impact hypothesis for lunar origin. Remarkably similar oxygen isotopic compositions between Earth and Moon samples support concepts that both bodies formed from identical material reservoirs, as anticipated if our Moon originated from Earth-orbiting debris created through giant impact events. However, subtle variations in alternative isotopic systems hint at more intricate processes operating during lunar formation. Certain elements display minor yet measurable differences between terrestrial and lunar compositions, suggesting impact events may have involved more than straightforward mixing of terrestrial and impactor materials. High-temperature processes during collision may have triggered isotopic fractionation, leaving distinctive signatures within the resulting moon. The concealed hemisphere's ancient materials also maintain evidence of our moon's earliest magnetic field. Paleomagnetic investigations of highland specimens revealed that the moon possessed surprisingly robust magnetic fields during its initial billion years, comparable in intensity to Earth's current field. This ancient magnetosphere would have supplied protection against solar wind erosion and cosmic ray bombardment, potentially preserving volatile materials that might otherwise have escaped into space. Discovery of this ancient magnetic field raises fundamental questions about lunar early thermal conditions and interior dynamics. Producing planetary magnetic fields requires convection within electrically conducting fluids, typically molten metals in planetary cores. Our moon's compact size should have led to rapid cooling and core solidification. Yet paleomagnetic evidence suggests core convection continued much longer than simple thermal models would anticipate. One potential explanation involves gravitational stirring caused by changing lunar orbital distance from Earth. Early in history, our moon orbited much closer to our planet while experiencing stronger tidal forces that could have supplied additional energy driving core convection. As the moon gradually migrated away from Earth through tidal friction, this supplementary energy source would have diminished, eventually permitting core solidification and magnetic field generation cessation. Timing of magnetic field decay recorded in lunar rocks of varying ages supplies crucial constraints on early Earth-Moon evolutionary models. Through investigating magnetic signatures preserved within specimens from different lunar regions and temporal periods, researchers can reconstruct core dynamics history and orbital evolution with unprecedented detail. The hidden hemisphere's magnetic anomalies also offer perspectives into impact-related magnetic field production. Some of our moon's strongest magnetic signatures appear in regions antipodal to major impact basins, indicating basin-forming impacts may have temporarily enhanced magnetic field strength through shock-related mechanisms. These impact-generated magnetic fields could have persisted for millennia after initial collisions, leaving permanent magnetization within crustal materials. Understanding these mechanisms carries implications for magnetic field generation on alternative planetary bodies, particularly smaller worlds that might not sustain long-lived magnetic fields through conventional core dynamo processes. Mars, for example, shows evidence of ancient magnetic fields potentially generated through similar impact-related mechanisms. Water exploration on the lunar hidden hemisphere has revealed deposits potentially transforming our space exploration approach. While most abundant ice deposits exist in permanently shadowed polar craters, smaller concentrations have been detected throughout far-side highlands. These broadly distributed water reservoirs suggest volatile delivery to our moon was a global process rather than being restricted to polar regions. Water discovery in unexpected locations challenges our understanding of how volatiles behave within lunar environments. Traditional models predicted that water molecules would quickly escape into space from most lunar surface areas due to low gravity and vacuum conditions. However, recent observations suggest that water can become trapped within mineral structures or migrate to cold regions where it remains stable for extended periods. This expanded understanding of lunar water distribution has significant implications for future exploration missions and resource utilization strategies. Rather than being limited to polar regions for water access, future lunar bases could potentially extract water from deposits scattered across the hidden hemisphere, providing greater flexibility in site selection and operational planning. These substances establish natural testing environments for comprehending how rocky compositions react under extreme pressure and temperature circumstances. Investigations of far-side collision melts have exposed intricate connections between shock forces, thermal conditions, and mineral alterations. Certain minerals demonstrate evidence of compression to pressures surpassing those discovered deep within planetary cores, while others maintain textures showing rapid cooling from temperatures far exceeding their fusion points. These severe circumstances generated novel mineral phases and crystalline formations that supply perspectives into fundamental materials science alongside planetary collision mechanisms. Conservation of these shock characteristics on the concealed hemisphere contrast dramatically with their widespread absence from Earth, where weathering and geological processes have eliminated most traces of ancient impacts. Our moon's hidden territory, therefore, functions as an exceptional information repository about collision mechanisms that sculpted all rocky planets during our solar system's violent infancy. As we approach the threshold of lunar exploration's new epoch, the concealed hemisphere beckons with promises of revelations potentially transforming our comprehension of planetary science, cosmology, and humanity's universal position. The mysterious hemisphere remaining enigmatic throughout human history until recent decades continues exposing secrets, challenging our most basic assumptions about world formation and development. Technological capabilities enabling far-side exploration's next phase are rapidly progressing. Robotic systems capable of autonomous operation within harsh lunar conditions are becoming increasingly sophisticated. Communication technologies are evolving to support complex operations on our moon's hidden hemisphere, while power systems designed for extended lunar night operations approach practical deployment. Life support technologies for eventual human exploration continue maturing. Scientific instruments planned for future far-side missions represent quantum advances beyond current capabilities. Advanced spectrometers will identify mineral compositions with unprecedented accuracy, while ground-penetrating radars will chart subsurface formations to kilometer depths. Seismometer networks will monitor moonquakes while providing detailed lunar interior imagery, as sample return missions will retrieve carefully selected materials for terrestrial laboratory analysis. However, perhaps future far-side exploration's most thrilling aspect lies in its potential to answer questions we haven't yet learned to formulate. Each fresh discovery about the hidden hemisphere has unveiled unexpected complexity while opening new investigation pathways. As our instruments become more sophisticated and our far-side presence becomes more sustained, we can anticipate encountering phenomena requiring entirely new understanding frameworks. Our moon's concealed hemisphere stands as testimony to exploration's power in expanding human knowledge while challenging our universal preconceptions. From a mysterious hidden hemisphere glimpsed in blurry photographs, it has emerged as one of our solar system's most scientifically valuable locations, offering unique perspectives into planetary formation, cosmic evolution, and life potential beyond Earth. As missions continue peeling back lunar mystery layers, each new revelation adds depth to our comprehension, while simultaneously showing how much we must still learn. The concealed hemisphere remains a frontier in the truest sense, the place where the next observation or specimen analysis might revolutionize our understanding of fundamental processes operating throughout the universe. The hidden hemisphere that has observed Earth for billions of years, unseen and unknown, is finally beginning to expose its secrets. As we continue exploring this alien yet familiar world, we discover that our moon's concealed side isn't just a destination for scientific discovery, but a mirror reflecting our own curiosity, ingenuity, and endless desire to understand our cosmic position. The collaboration between NASA and international space agencies in studying the concealed hemisphere has produced discoveries reading like chapters from a cosmic detective story. Each mission has contributed crucial puzzle pieces spanning billions of years, revealing narratives of violence, transformation, and preservation that challenge our understanding of world evolution. NASA's Lunar Reconnaissance Orbiter has functioned as our steadfast guardian, monitoring the concealed hemisphere with instruments so sensitive they can detect temperature variations smaller than a single degree, while mapping surface features down to small boulder sizes. For over a decade, this tireless observer has catalogued every crater, ridge, and mysterious bright ray streaking across ancient terrain. Its cameras have captured imagery of Chinese landers touching down on alien soil, documenting humanity's expanding presence on this hidden world with cosmic historian precision. Yet it's the data flowing from these observations that truly illuminates far-side secrets. The Lunar Orbiter Laser Altimeter aboard this spacecraft has measured lunar topography with such precision that scientists can now create three-dimensional models accurate within centimeters. These measurements reveal landscapes sculpted by forces so violent they defy imagination, where collision craters overlap like frozen pond ripples, each narrating stories of cosmic collisions that shook our moon to its core. Thermal mapping conducted by the Diviner instrument has unveiled temperature patterns speaking to our moon's complex relationship with solar energy and its internal structure. Certain far-side regions maintain temperatures hundreds of degrees different from their surroundings, hinting at compositional differences potentially reflecting our moon's tumultuous formation history. These thermal anomalies create evolutionary heat maps, showing where ancient impacts brought deep materials to surfaces and where volcanic processes left lasting signatures. Perhaps most intriguingly, neutron detectors aboard various lunar missions have identified hydrogen signatures scattered across far-side landscapes. These hydrogen concentrations often appear in most unlikely places, distant from permanently shadowed polar regions where water ice was expected to concentrate. Distribution of these signals suggests our moon's interaction with solar wind and cosmic bombardment has been creating and preserving water molecules in ways unanticipated by early lunar models. The discovery that water might exist in forms and locations beyond our initial expectations carries profound implications for understanding not just our moon, but broader processes distributing volatiles throughout our solar system. If water can be preserved in lunar highlands through mechanisms we're only beginning to comprehend, similar processes might operate on other airless bodies throughout our cosmic neighborhood. Asteroids, outer planet moons, and even distant exoplanet surfaces might harbor water reservoirs, supporting future exploration or even life itself. Recent laboratory analysis of lunar specimens has revealed another mystery layer in the Farside story. When scientists subject these ancient materials to increasingly sophisticated analytical techniques, they uncover isotopic fingerprints that don't match any substances found elsewhere in our solar system. Certain elements show ratios suggesting these materials formed under extreme heat and pressure conditions, possibly during our moon's earliest molten phase when the entire body existed as a magma ocean. Other isotopic anomalies hint at more exotic processes. Certain rare elements appear in concentrations only explicable by cosmic ray bombardment across billions of years, or possibly through incorporating materials from impacting bodies that created our moon's largest craters. Each rock specimen becomes a time capsule, preserving information about events occurring when our solar system was young and chaotic, when massive objects routinely collided and reshaped entire worlds. Seismic studies of our moon continue yielding surprises, challenging our understanding of planetary interiors. When Apollo-era seismotors detected moonquakes and collision events, they recorded vibrations behaving unlike anything observed on Earth. Seismic waves would ring through lunar interior for remarkably extended periods, creating patterns leading some researchers to describe our moon as ringing like a bell when struck. This unusual seismic behavior suggests our moon's interior possesses unique properties potentially related to its formation through giant impact or subsequent evolution under Earth's gravitational influence. Modern reanalysis of these seismic records using advanced computational techniques is revealing previously hidden details about lunar internal structure. The data suggests our moon may possess a partially molten core surrounded by solid mantle layers with complex compositional variations. These internal differences may explain why seismic waves propagate differently through various lunar regions, and why magnetic field generation persisted longer than simple thermal models would predict. This extraordinary seismic conduct initially triggered speculation regarding our moon's internal architecture. Could extended resonance indicate lunar partial hollowness, as sensational media headlines proposed? More comprehensive analysis unveiled a more sophisticated explanation. Our moon's interior appears extensively fractured while possibly containing zones of varying density and composition affecting seismic wave propagation patterns. Rather than suggesting hollow interior spaces, these characteristics indicate complex internal architecture shaped by billions of years of collision bombardment and thermal development. The concealed hemisphere's function in maintaining this seismic information proves essential because it experiences different collision bombardment patterns compared to the near side. The hemisphere facing away from Earth receives impacts from objects arriving from deep space, while the near side remains partially protected by Earth's gravitational influence. This bombardment flux difference creates distinctive seismic fingerprints, helping scientists comprehend how bombardment patterns have fluctuated throughout lunar chronology. Contemporary computer modeling now permits researchers to simulate these ancient moonquakes with extraordinary precision, incorporating everything from lunar internal structure to collision event dynamics. When these models undergo comparison with actual seismic documentation preserved in Apollo-era data, They expose insights about lunar formation and development unobtainable through alternative methods. The concealed hemisphere functions as a natural seismograph, documenting and maintaining information about cosmic impacts occurring billions of years ago. Magnetic field investigations of the lunar concealed hemisphere have revealed perhaps the most perplexing aspects of lunar development. Materials from the concealed hemisphere preserve some of the most powerful magnetic fingerprints discovered anywhere on our moon, indicating this hemisphere experienced intense magnetic fields during specific lunar history periods. These paleomagnetic documentations suggest our moon once possessed a global magnetic field, potentially comparable in intensity to Earth's current field. This ancient lunar magnetosphere's existence raises fundamental questions about our moon's early thermal condition and interior dynamics. Producing planetary magnetic fields typically requires convection in molten metallic cores driven by cooling and crystallization of iron-rich substances. Our moon's compact size should have resulted in rapid cooling and core solidification, yet magnetic evidence indicates core convection continued for hundreds of millions of years longer than simple thermal models would anticipate. The concealed hemisphere's magnetic anomalies also display spatial arrangements correlating with major collision structures. Some of the most powerful magnetic fingerprints are located at positions directly opposite large impact basins, indicating basin-forming impacts may have enhanced magnetic field production through shock-related mechanisms. When massive asteroids strike one side of planetary bodies, shock waves converge at antipodal points, potentially creating conditions enhancing magnetic field intensity or preserving existing magnetization more effectively. Comprehending these magnetic mechanisms carries implications extending far beyond lunar science. Many small planetary bodies throughout our solar system demonstrate evidence of ancient magnetic fields unexplainable through conventional core dynamo processes. Our moon's magnetic chronology may supply a template for understanding how magnetic fields are produced and maintained on worlds lacking the size and thermal energy sustaining long-lived core convection. Resource exploration on the lunar concealed hemisphere has unveiled deposits potentially revolutionizing space exploration. Beyond water ice discovered in permanently shadowed craters, orbital surveys have identified concentrations of rare earth elements, titanium and other valuable substances scattered across farside landscapes. These resource charts, created by combining data from multiple missions, demonstrate that our moon's hidden hemisphere contains materials supporting extensive space-based industrial operations. Distribution of these resources reflects our moon's complex geological chronology. Rare earth elements appear concentrated in regions where ancient impacts brought deep crustal materials to surfaces. Titanium-rich minerals exist in areas where unique volcanic processes operated billions of years ago. Iron and other metals show concentrations correlating with large collision event locations, possibly representing fragments of metallic impactors themselves. However, perhaps the most fascinating resource discovery involves detecting helium-3, a rare isotope potentially serving as fuel for advanced fusion reactors. This material, deposited on lunar surfaces through billions of years of solar wind bombardment, exists in concentrations making lunar mining economically feasible. The concealed hemisphere's atmospheric protection absence means it has accumulated helium-3 throughout its entire geological chronology, creating reserves potentially powering human civilization for millennia. Technical challenges of extracting and processing lunar resources are substantial yet surmountable. Robotic mining systems capable of operating in harsh lunar conditions are under development, while processing techniques for separating valuable materials from lunar regolith undergo testing in terrestrial laboratories. Reduced gravity and atmospheric interference absence on our moon could actually simplify some industrial processes compared to terrestrial counterparts, particularly those involving high-temperature operations or toxic material handling. Economic implications of lunar resource extraction extend beyond simple material wealth. Access to space-based resources could fundamentally transform space exploration economics, enabling spacecraft, habitat, and infrastructure construction using materials that don't require launching from Earth's deep gravity well. A space-based industrial economy could enable Mars and outer planet missions that would be prohibitively expensive using Earth-based resources exclusively. Environmental considerations of lunar mining present unique challenges and opportunities. Unlike terrestrial mining, lunar resource extraction wouldn't directly impact ecosystems or atmospheric composition. However, preserving scientifically valuable lunar sites and preventing mining operation contamination requires careful planning and international coordination. Our moon's function as a natural laboratory for studying planetary processes could be compromised if mining operations aren't conducted with appropriate safeguards. The concealed hemisphere's potential as an astronomical observatory location continues driving mission planning at space agencies worldwide. Natural radio silence created by our moon's blocking effect represents one of the inner solar system's most valuable scientific resources. This electromagnetic quiet zone becomes increasingly precious as Earth's radio interference grows with advancing technology and expanding satellite networks. Proposed astronomical facilities for the concealed hemisphere range from individual specialized instruments to comprehensive observatory complexes, potentially revolutionizing multiple astronomy fields. Radio telescopes operating from this unique location could observe frequencies completely blocked by Earth's ionosphere, opening observational windows into cosmic phenomena invisible from terrestrial locations. The permanently shadowed regions scattered across the concealed hemisphere offer additional advantages for certain astronomical observations. These areas maintain extremely stable temperatures, creating ideal conditions for infrared detectors and other sensitive instruments requiring thermal stability. Future lunar missions are incorporating increasingly sophisticated scientific instruments designed to exploit the concealed hemisphere's unique properties. Advanced spectrometers will analyze mineral compositions with unprecedented precision, while ground-penetrating radars will map subsurface structures to depths previously unattainable. Sample return missions planned for the concealed hemisphere will target specific geological formations identified through orbital reconnaissance, bringing back carefully selected specimens for detailed terrestrial laboratory analysis. These samples will help answer fundamental questions about lunar formation, early solar system bombardment, and the processes that created the dramatic hemispheric differences we observe today. International cooperation in lunar exploration has become essential as missions become more complex and expensive. Space agencies worldwide are pooling resources and expertise to tackle the technical challenges of sustained far-side operations, while sharing the scientific discoveries and technological advances that result. This collaborative approach ensures that the benefits of lunar exploration extend beyond individual nations, contributing to global scientific knowledge and technological capabilities. The legal and regulatory frameworks governing lunar resource extraction are still evolving, requiring international dialogue to ensure fair access to lunar resources while protecting sites of scientific or historical significance. As we stand on the threshold of humanity's return to our moon, the concealed hemisphere represents both our greatest scientific opportunity and our most significant technical challenge. The secrets preserved in its ancient rocks, its unique observational advantages, and its untapped resource potential make it one of the most valuable destinations in our solar system. Radio telescopes functioning at frequencies obstructed by Earth's ionosphere could identify transmissions from cosmic dawn periods, the epoch between universal initial cooling and inaugural stellar formation. Optical telescopes liberated from atmospheric interference could execute precision measurements of stellar positions and planetary movements with accuracy unachievable from terrestrial installations. Technical specifications for these astronomical installations challenge current robotics and space construction technology boundaries. Establishing kilometer-scale antenna networks or reflector assemblies on lunar terrain would demand autonomous systems capable of exact construction operations without direct human oversight. The severe lunar environment, featuring extreme temperature fluctuations and abrasive particles, generates additional obstacles for maintaining delicate scientific equipment across extended durations. Power production for far-side observatories presents particular difficulties due to prolonged lunar darkness periods. Solar arrays alone cannot supply continuous energy during 14-day lunar nights, necessitating energy storage systems or alternative power sources such as nuclear generators. Developing reliable long-duration power systems for lunar operations carries applications beyond astronomy, potentially enabling sustained human presence and industrial operations throughout our solar system. Scientific returns from far-side astronomical observations could validate substantial required investments. The capability to observe previously inaccessible radio frequencies would unveil entirely new universal windows, potentially exposing phenomena remaining completely unknown to contemporary astronomy. Detecting transmissions from cosmic dawn periods could supply direct information about the universe's earliest epochs, complementing and extending space-based telescope capabilities, observing in optical and infrared wavelengths. Coordination required for international lunar astronomical installations presents both obstacles and opportunities for space cooperation. No individual nation possesses all resources necessary for constructing and operating major lunar observatories, making international collaboration essential for success. Developing shared lunar infrastructure could serve as a model for future cooperative ventures throughout our solar system, fostering peaceful cooperation in space exploration while advancing scientific knowledge for all humanity. Cultural and philosophical implications of far-side exploration extend beyond scientific discovery into questions about humanity's relationship with the cosmos. For millennia, our moon has functioned as a symbol of mystery, transformation, and the unknown. The hidden hemisphere represented the ultimate frontier, a realm existing beyond human perception and imagination. Now that we're beginning to explore and comprehend this concealed world, we're confronting fundamental questions about discovery's nature and human knowledge limitations. The far side's transformation from mythical realm to scientific laboratory reflects humanity's evolving relationship with the unknown. Where ancient cultures perceived divine mystery, modern science discovers natural processes operating according to physical laws. Yet this scientific understanding doesn't diminish discovery's wonder moksha. It amplifies it by revealing the true scale and complexity of processes that shaped our cosmic neighborhood. Lunar exploration democratization through international cooperation and commercial space ventures creates opportunities for broader participation in far-side discovery. Amateur astronomers contribute observations complementing professional missions, while citizen science projects allow individuals worldwide to participate in analyzing lunar data and identifying new phenomena. This broader engagement helps ensure lunar exploration benefits extend beyond academic institutions to inspire and educate people throughout the world. Far-side exploration's educational value cannot be overstated. Students following current missions learn firsthand how scientific knowledge develops through careful observation, hypothesis testing, and international collaboration. Modern space missions' real-time nature allows people worldwide to experience discovery excitement as it unfolds, creating emotional connections to scientific exploration lasting lifetimes. Far-side exploration challenges also serve as catalysts for technological innovation with applications far beyond space exploration. Autonomous systems developed for lunar operations advance robotics technology with applications in manufacturing, healthcare, and environmental monitoring. Communication systems required for far-side missions improve satellite technology and deep space navigation. Life support and resource utilization technologies needed for sustained lunar operations contribute to Earth's sustainability efforts. As we look toward far-side exploration's future, the discovery trajectory seems poised to accelerate dramatically. Multiple space agencies and commercial organizations are developing missions expanding our presence on the hidden hemisphere. Advanced robotic systems will conduct increasingly sophisticated scientific investigations, while human explorers may eventually establish permanent research stations enabling continuous observation and experimentation. Integrating artificial intelligence and machine learning into far-side exploration will amplify human capabilities and enable discoveries potentially missed by traditional analytical approaches. Automated systems will monitor lunar environments continuously, identifying transient phenomena and unusual patterns requiring further investigation. Machine learning algorithms will analyze vast data sets collected by orbital missions, potentially revealing subtle correlations and trends escaping human notice. The far side's role as a stepping stone to deeper space exploration becomes increasingly apparent as mission planners develop strategies for Mars exploration and outer planet missions. Our moon's lower gravity and atmospheric resistance absence make it an ideal location for launching and refueling deep space missions. Far-side facilities could serve as staging areas for interplanetary expeditions, providing infrastructure and resources needed for sustained exploration throughout our solar system. Lessons learned from far-side exploration will inform our understanding of other mysterious worlds throughout the universe. Techniques developed for studying our moon's hidden hemisphere will be applicable to investigations of asteroids, comets, and outer planet moons. Scientific frameworks created to interpret far-side geology will help us understand planetary processes operating on worlds orbiting distant stars. However, perhaps far-side exploration's most profound impact lies in its potential to reshape our perspective on Earth itself. Observing our planet from our moon's far side, suspended in space's blackness as a brilliant blue marble, provides perspective on our world's uniqueness and fragility that no description can convey. This cosmic perspective, available to only a handful of Apollo astronauts previously, may become increasingly accessible as far-side exploration expands. The hidden hemisphere, remaining mysterious throughout human history, continues yielding secrets challenging our understanding while inspiring imagination. Each new discovery adds knowledge depth while simultaneously revealing how much remains to be learned. The far side stands as both destination and symbol, representing humanity's endless quest to understand our universal place, while demonstrating our capacity to transform the unknown into familiar through careful observation and analysis. As robotic explorers continue their patient work in lunar landscapes and human explorers prepare for their return to our moon, the far side awaits with secrets preserved for billions of years. Whether these secrets involve ancient impact processes, exotic mineral formations, or resources potentially transforming space exploration, they represent discovery opportunities that could reshape our understanding of planetary science and our space future. Our moon's far side, once the realm of speculation and imagination, has become humanity's newest frontier for scientific discovery and technological achievements. As we continue exploring this alien yet familiar world, we discover that each answer leads to new questions. Each solved mystery reveals deeper complexities, and each technological achievement opens pathways to even greater challenges and opportunities. The journey into our moon's hidden hemisphere has transformed from impossible dream to ongoing reality, demonstrating humanity's remarkable capacity to push beyond perceived limitations and explore realms once thought forever beyond reach. This transformation reflects not just technological progress, but humanity's fundamental drive to explore, understand, and push the boundaries of the possible. The far side represents more than scientific opportunity. It embodies human potential to transform the mysterious into the known, the impossible into the achievable, and the alien into the familiar through persistence, ingenuity, and collaborative effort. Every revelation unveils fresh investigation pathways, while missions progressively advance our comprehension of intricate mechanisms that molded our solar system and persistently shape our cosmic destiny. Beneath distant stellar illumination, the concealed hemisphere maintains its eternal watch, safeguarding narratives of cosmic brutality and planetary genesis occurring during our solar system's infancy. Currently, for the inaugural time across its 4.5 billion-year existence, this obscured realm possesses human observers of its mysteries. As we master interpreting chronicles inscribed within its primordial materials and maintained across its collision-marked terrain, we realize our moon's hidden territory isn't merely an exploration target, but a connection linking us to cosmic evolution's profound enigmas and our stellar origins. Engineering achievements facilitating our investigation of this concealed domain continuously expand boundaries of what seemed achievable within space's hostile environment. Penetrating deeper into the concealed hemisphere's puzzles, we confront construction obstacles appearing impossible mere decades ago. Contemporary robotic investigators navigate these barriers with extraordinary sophistication. Contemplate the intricate coordination executed by NASA's Deep Space Communication Network, maintaining contact with missions venturing beyond lunar protective influence. When spacecraft vanish behind lunar horizons, ground operators must depend on meticulously orchestrated orbital mechanics, re-establishing communication hours later. This celestial concealment game demands split-second precision and mathematical accuracy, showcasing humanity's expanding mastery of astronomical navigation. Instruments aboard these distant explorers represent miniaturization and durability marvels. Spectrometers smaller than footwear can determine rock chemical composition from orbit, while cameras possessing resolution capable of detecting dining furniture from hundreds of kilometers above surfaces capture imagery revealing our moon's hidden topography with stunning clarity. These technological accomplishments, emerging from studying an unreachable world's necessity, frequently return to Earth in applications benefiting all humanity. Data flows returning from the concealed hemisphere create increasingly comprehensive portraits of a world defying straightforward classification. Recent orbital investigations have exposed mineral distributions following patterns unlike anything discovered on the familiar near side. Rare element concentrations appear in unexpected locations, often connected with ancient collision structures excavating materials from deep lunar interior regions. These mineral charts narrate stories of cosmic violence and geological mechanisms operating under conditions vastly different from terrestrial experiences. When enormous asteroids impacted the young moon billions of years ago, they didn't merely generate craters, no, they fundamentally transformed chemical landscapes, mixing materials from various depths while creating deposits preserving information about lunar interior composition through methods impossible to achieve otherwise. Rare earth elements distributed across far-side terrain represent more than scientific curiosities. These materials, essential for contemporary electronics and advanced technologies, exist in concentrations, potentially supporting future space-based manufacturing. Extracting these resources from lunar surfaces, while technically demanding, offers enticing possibilities for reducing humanity's dependence on terrestrial mining activities. However, perhaps more captivating than known resources are materials we haven't yet identified. Each fresh spectroscopic investigation reveals previously undetected mineral phases and chemical compounds, expanding our understanding of planetary formation process possibilities. Some exotic materials may have formed under pressure and temperature circumstances existing nowhere else in our solar system, establishing natural laboratories for investigating extreme physics. The concealed hemisphere's thermal environment presents fascinating complexities. Without Earth's reflected sunlight's moderating influence, hidden hemisphere temperatures can descend to depths approaching absolute zero in permanently shadowed areas. These cosmic freezers preserve volatile materials rapidly sublimating elsewhere, establishing natural repositories for studying early solar system chemical inventories. Temperature anomaly discoveries scattered across far-side landscapes hint at subsurface mechanisms remaining poorly understood. Certain regions maintain temperatures significantly different from surroundings, possibly indicating underground thermal sources or unusual thermal conductivity within lunar regolith. These thermal fingerprints create underground weather charts revealing how thermal energy flows through lunar interior in ways surface observations alone could never detect. Our moon's seismic mysteries continue perplexing researchers decades after Apollo missions initially deployed sensitive earthquake detectors on lunar terrain. The peculiar manner moonquakes propagate through lunar interior suggests structural complexities, challenging our understanding of planetary body formation and evolution. Rather than simple layered architecture early models predicted, our moon appears possessing internal structure, including zones of different density, composition, and possibly voids created by ancient collision events. These seismic anomalies become increasingly intriguing when examined within the concealed hemisphere's unique bombardment chronology. The hidden territory has experienced different impact patterns than the near side, receiving projectiles from deep space arriving with different velocities and compositions than those striking the Earth-facing side. This asymmetric bombardment may have generated internal structures varying between hemispheres, contributing to seismic signatures making our moon resonate like struck metal when meteorites impact it. Recent computer modeling of these ancient collision events reveals processes so violent they challenge imagination. When asteroids traveling dozens of kilometers per second struck the early moon, they didn't simply excavate craters, it transmitted shock waves racing through the entire lunar body, generating pressure pulses temporarily liquefying solid rock, while producing temperatures exceeding those found in stellar cores. Reverberations from these cosmic collisions may have established internal structures continuing to influence seismic wave propagation through our moon today. Magnetic field investigations of lunar materials have unveiled another mystery layer in the concealed hemisphere narrative. Ancient magnetism preserved in highland specimens suggests our moon once possessed a global magnetic field potentially rivaling Earth's in intensity. This revelation overturned previous assumptions about small planetary body thermal evolution, while raising fundamental questions about magnetic field generation and maintenance. The strength and longevity of this ancient lunar magnetosphere, implies our moon's early interior remained much more thermally active than conventional models predicted. Generating planetary magnetic fields requires convection in electrically conducting fluids, typically molten metallic cores driven by cooling and crystallization processes. Our moon's compact dimensions should have resulted in rapid thermal dissipation and core solidification, yet paleomagnetic evidence indicates magnetic field generation persisted for hundreds of millions of years longer than thermal models suggested possible. This extended magnetic activity period may reflect unique circumstances during our moon's formation and early evolution. The giant impact hypothesis for lunar origin suggests our moon formed from debris ejected when a Mars-sized object collided with primordial Earth. This catastrophic event would have left our moon initially molten, with a core that might have remained liquid longer than expected due to tidal heating from Earth's gravitational influence. During our moon's early history, it orbited much closer to Earth, experiencing stronger tidal forces, potentially providing additional energy-sustaining core convection. The gradual orbital recession caused by tidal friction would have slowly reduced this energy input, eventually permitting core solidification and magnetic field cessation. This scenario explains both the initial strength of lunar magnetic fields and their eventual disappearance. Magnetic anomalies preserved across the concealed hemisphere also display spatial patterns correlating with major collision structures. Some of the most powerful magnetic signatures appear at locations directly opposite large impact basins, indicating basin-forming impacts may have enhanced magnetic field generation through shock-related mechanisms. When massive asteroids strike planetary bodies, shock waves converge at antipodal points, potentially creating conditions amplifying magnetic field intensity or preserving existing magnetization more effectively. Understanding these processes carries implications extending far beyond lunar science, potentially explaining magnetic signatures observed on other small planetary bodies throughout our solar system. The concealed hemisphere appears maintaining some of the most robust magnetic fingerprints discovered anywhere on our moon, potentially because thicker crustal layers supplied superior protection for these primordial magnetic documentation. Certain investigators propose that magnetic fields themselves may have influenced hemispheric disparities we observe currently, affecting how solar wind particles interacted with lunar terrain while potentially impacting volatile material retention across different zones. Connections between magnetic anomalies and major collision structures indicate basin-forming impacts may have participated in magnetic field production or conservation. When enormous impactors struck our moon, they potentially generated temporary magnetic fields through shock-induced mechanisms or amplified existing fields through complex electromagnetic interactions. Comprehending these mechanisms could supply perspectives into magnetic field production on alternative worlds throughout our solar system. The concealed hemisphere's water narrative continues developing as increasingly sophisticated detection techniques reveal complex methods hydrogen and oxygen storage occurs within lunar environments. Beyond obvious ice accumulations in permanently shadowed craters, investigators have identified water signatures within mineral structures bound inside crystal lattices and possibly as thin layers on grain surfaces throughout highland territories. This extensive water distribution in various forms indicates our moon's interaction with solar wind particles and cosmic bombardment has been generating and preserving water molecules through multiple pathways across billions of years. Solar wind continuously deposits hydrogen atoms onto lunar surfaces where they can interact with oxygen-bearing minerals forming hydroxyl groups and eventually water molecules. While most water rapidly escapes to space, some becomes trapped within mineral structures or migrates toward cold regions where accumulation occurs over geological timescales. This distributed water resources implications extend far beyond simple resource utilization. Water presence in unexpected forms and locations suggests similar mechanisms may operate on other airless bodies throughout our solar system. Asteroids, outer planet moons, and even distant exoplanet surfaces might harbor water reserves created through analogous mechanisms, potentially expanding worlds that could support future exploration or life itself. Chemical diversity revealed through far-side material analysis continues challenging our understanding of planetary formation mechanisms. Specimens returned by recent missions display isotopic fingerprints, not matching any materials discovered elsewhere in our solar system, suggesting our moon may have experienced unique evolutionary mechanisms operating under conditions unlike those on other worlds. Some chemical anomalies appear related to our moon's formation through giant impact events, while others may reflect subsequent processing by cosmic bombardment, solar wind implantation, or internal differentiation mechanisms. Each unusual isotopic ratio or unexpected elemental concentration supplies clues about conditions existing during different lunar history periods, helping investigators reconstruct complex event sequences that shaped our nearest celestial neighbor. These chemical signature preservation on the concealed hemisphere may relate to the hemisphere's different geological chronology. Limited volcanic activity on the hidden side meant fewer ancient materials were buried or modified by later geological mechanisms, establishing a chemical archive preserving information about our moon's earliest epochs. This conservation makes the concealed hemisphere particularly valuable for understanding not just lunar evolution, but broader mechanisms that shaped all terrestrial planets during our solar system's violent youth. Atmospheric investigations of the lunar concealed hemisphere have unveiled another unexpected aspect of this supposedly airless world. While our moon lacks substantial atmosphere in conventional terms, it possesses an extremely tenuous gas envelope varying in composition and density depending on location and timing. The concealed hemisphere contributes unique components to this minimal atmosphere through mechanisms differing from those operating on the near side. Solar wind particles striking concealed hemisphere surfaces liberate atoms and molecules through sputtering mechanisms, while thermal cycling between lunar day and night drives sublimation and deposition of volatile materials. Micrometeorite impacts continuously vaporize small surface material quantities, adding contributions to our moon's gossamer atmosphere. These mechanisms create dynamic, ever-changing atmospheric environments that, while incredibly thin by terrestrial standards, play important roles in transporting materials across lunar surfaces. Understanding our moon's minimal atmosphere carries implications for future exploration and resource utilization. Even trace atmospheric gas amounts can affect sensitive scientific instruments, while dust particles suspended in thin atmosphere could pose hazards to equipment and human explorers. Lunar dust's electrostatic properties, enhanced by solar wind charging effects, create additional challenges for operations in lunar environments. Ongoing geological activity on our moon, while minimal compared to Earth, continues shaping concealed hemisphere landscapes in subtle yet measurable ways. Thermal expansion and contraction create stress fractures in surface rocks, while gradual sublimation of subsurface ice deposits can cause small-scale surface changes. These mechanisms operate so slowly their effects are barely perceptible over human timescales, but accumulate over millions of years, creating measurable lunar landscape modifications. Recent observations have identified fresh crater rays and impact features, providing evidence for ongoing concealed hemisphere bombardment by micrometeorites and larger objects. While major impacts are rare in current epochs, continuous rain of smaller projectiles gradually modifies surface features, while mixing uppermost lunar regolith layers. This space weathering process creates characteristic appearances of lunar highland materials, while affecting preservation and accessibility of resources like water ice and rare minerals. Tidal effects locking our moon in synchronous rotation with Earth continue influencing the concealed hemisphere through subtle gravitational forces, creating stress patterns in lunar crust. These tidal stresses, while much weaker than those originally shaping our moon's rotation, may contribute to occasional moonquakes detected by seismic monitoring systems. The concealed hemisphere experiences these tidal forces differently than the near side due to greater Earth distance, potentially contributing to structural differences observed between hemispheres. The concealed hemisphere's role in the broader Earth-Moon system continues evolving as tidal friction gradually increases distance between our planet and its natural satellite. This slow orbital evolution affects gravitational relationships between Earth and Moon, potentially influencing everything from tidal patterns in Earth's oceans to our Moon's rotational stability. Understanding these long-term changes helps investigators predict how the Earth-Moon system will continue evolving over astronomical timescales. Farside exploration's cultural impact extends beyond scientific discovery into art, literature, and human imagination realms. Our moon's hidden hemisphere transformation from mystery and speculation realm into scientific investigation destination reflects humanity's evolving relationship with the unknown. Where previous generations could only imagine what existed beyond lunar horizons, we now possess detailed charts and chemical analyses of this alien landscape. This transformation from mystery to knowledge doesn't diminish discovery's wonder mine. Instead, it reveals natural process complexity and beauty, operating on scales dwarfing human experience. The concealed hemisphere has become a symbol of human achievement, demonstrating our species' remarkable capacity to transform the impossible into the achievable through persistence, ingenuity, and international cooperation. This transformation reflects not merely technological progress, but humanity's fundamental drive to explore, understand, and expand the boundaries of the possible. Contemporary students following far-side missions experience discovery excitement firsthand, learning how scientific knowledge develops through careful observation, hypothesis testing, and collaborative effort. This educational value extends beyond formal academic settings, inspiring amateur astronomers and citizen scientists worldwide to participate in lunar discovery processes. The democratization of scientific participation through modern communication technologies allows individuals globally to contribute to lunar research, analyzing data, identifying anomalies, and proposing new hypotheses. This collaborative approach ensures far-side exploration benefits extend beyond professional scientific communities to inspire and educate people throughout our world. As we continue investigating our moon's concealed hemisphere, each revelation adds depth to our cosmic understanding, while simultaneously demonstrating how much remains to be discovered. The far side stands as both destination and symbol, representing humanity's endless quest to comprehend our universal position, while showcasing our capacity to transform the mysterious into the familiar through careful observation and analysis. The hidden hemisphere that remained enigmatic throughout human history has become our newest frontier for scientific revelation and technological achievement, promising discoveries that could reshape our understanding of planetary science and our future among the stars. The concealed hemisphere's primordial collision basins and untouched highland territories speak of cosmic episodes so brutal and transformative. They challenge our capacity to grasp the powers that sculpted our solar system's early chronology. Educational possibilities generated by concealed hemisphere exploration inspire fresh generations of scientists, engineers, and explorers who will advance humanity's mission to comprehend our cosmic surroundings. Students tracking current missions learn not merely facts regarding lunar geology and planetary science, but also about discovery processes, hypothesis examination, and international collaboration driving contemporary scientific investigation. Technological innovations demanded for concealed hemisphere exploration continue discovering applications in fields distant from space science. Autonomous systems created for lunar operations advance. Robotics technology with applications in manufacturing, healthcare, and environmental monitoring. Communication systems required for concealed hemisphere missions enhance satellite technology and deep space navigation capabilities. Material science breakthroughs needed for surviving harsh lunar conditions contribute to advances in everything from electronics to construction materials. As we approach an era witnessing sustained human presence on the concealed hemisphere, we're preparing to answer questions intriguing humanity for generations, while simultaneously discovering fresh mysteries we couldn't have imagined before beginning this exploration journey. The hidden hemisphere remaining beyond human reach throughout recorded history is becoming humanity's newest frontier, offering discovery opportunities that could reshape our understanding of planetary science and our stellar future. Our moon's concealed hemisphere represents more than a scientific investigation destination. It embodies humanity's capacity to transform impossibility into achievement through patience, ingenuity, and collaborative effort. Each successful mission to the hidden hemisphere demonstrates our growing ability, extending reach beyond our home planet boundaries, while each fresh discovery reminds us that the universe holds secrets we're only beginning to uncover. Tonight, as you rest beneath the familiar glow of our moon's near side, remember that just beyond that brilliant horizon lies a world of wonders. Our species is only now learning to explore. The same gravitational powers creating tides in Earth's oceans and stabilizing our planet's rotation have preserved for us a natural laboratory where cosmic evolution stories remain inscribed in stone, awaiting human curiosity and technological capability to finally decipher their ancient messages. The journey to comprehend the concealed hemisphere continues with each passing day, bringing fresh data from robotic explorers and new plans for future missions, expanding our presence on this alien yet familiar world. In cosmic time's grand sweep, our exploration of our moon's hidden hemisphere has barely commenced. Yet already we've learnt enough to transform our understanding of how worlds form, evolve, and preserve stories of their cosmic heritage. The concealed hemisphere awaits, patient and mysterious, holding secrets spanning our entire solar system's history. As we prepare for lunar exploration's next chapter, we carry accumulated wisdom of generations of astronomers, engineers, and dreamers who dared imagine humanity could one day venture beyond familiar earthly boundaries to explore wonders hidden among stars. As we drift deeper into this hidden world's exploration, we encounter discoveries pushing against planetary science possibility boundaries. Seismic mysteries recorded during Apollo eras continue perplexing researchers with haunting implications. When sensitive instruments detected moonquakes reverberating through lunar interior, they captured something defying every earthly comparison we possessed. Our moon, when struck by meteorite impacts or shaken by internal tremors, would resonate like a cosmic bell for hours, sometimes maintaining vibrational songs for periods stretching beyond reason. This prolonged resonance created speculation, whispers echoing through decades of scientific discourse. Could our celestial companion harbor vast hollow chambers within its ancient core? Data painted pictures of seismic waves traveling through interior so fractured and complex that researchers wondered whether conventional planetary formation models could account for such unusual behavior. Dr. Maurice Ewing, one of principal investigators analyzing these seismic fingerprints, famously remarked that lunar interior seemed behaving as though containing large void spaces or zones of drastically different density. Implications sent ripples through scientific communities, challenging fundamental assumptions about how worlds like ours are constructed. Yet as more sophisticated analysis techniques emerged, more nuanced understanding began taking shape. The concealed hemisphere's thicker crust appears playing crucial roles in these seismic anomalies. When shockwaves from impacts or moonquakes encounter dense highland materials dominating the hidden hemisphere, they propagate in ways creating prolonged resonance effects puzzling early researchers. Rather than indicating hollow chambers, these fingerprints likely reflect complex internal architecture shaped by billions of years of cosmic bombardment and thermal evolution. However, mystery deepens when considering asymmetric nature of these seismic patterns. Vibrations traveling through different lunar regions exhibit distinct characteristics, suggesting interior is far from uniform. Some pathways seem conducting seismic energy more efficiently than others, creating acoustic maps revealing structural variations invisible to surface observations. Implications extend beyond mere scientific curiosity. Understanding lunar internal architecture becomes crucial as we plan future exploration and resource extraction. Will drilling operations encounter void spaces or unusually dense materials? How will propagation of human-generated vibrations affect sensitive scientific instruments? These questions transform abstract seismic data into practical engineering considerations, influencing future lunar facility design. Recent computer simulations have begun modeling these seismic behaviors with increasing sophistication, incorporating everything from lunar formation history to individual impact event effects. Results suggest the concealed hemisphere's unique bombardment chronology may have created internal fracture networks extending deep into lunar interior. These fractures, invisible from surfaces but detectable through their influence on seismic wave propagation, represent scars from cosmic collisions so violent they permanently altered lunar internal structure. Preservation of these ancient fracture systems on the concealed hemisphere contrasts with near side where extensive volcanic activity may have filled or altered many internal voids. This difference in geological processing means the hidden hemisphere serves as more complete archive of lunar violent past, preserving structural evidence of events occurring during our solar system's most chaotic epochs. Volatile searches on the concealed hemisphere have revealed distribution patterns challenging our understanding of how water and other light elements behave in lunar environments. While most obvious concentrations exist in permanently shadowed polar craters, orbital surveys have detected hydrogen signatures scattered throughout highland regions where conventional models suggest such material should have escaped to space long ago. These unexpected volatile deposits appear, following patterns correlating with ancient collision structures, suggesting cosmic collisions may have created local environments capable of preserving water and other light elements over geological timescales. Some craters seem acting as natural cold traps even when not permanently shadowed, maintaining temperatures low enough preventing rapid ice deposit sublimation. Discovery of these distributed water resources transforms our understanding of lunar resource potential. Rather than being restricted to polar regions for water access, future missions might tap widely scattered deposits supporting exploration activities throughout the concealed hemisphere. This geographical flexibility would allow mission planners choosing landing sites based on scientific value or strategic importance, rather than being constrained by resource availability. However, the most intriguing aspect of concealed hemisphere water distribution lies in its potential origins. Isotopic analysis of lunar ice specimens reveals fingerprints not matching terrestrial water, suggesting at least some of our moon's volatile inventory may have been delivered by comets and asteroids during late heavy bombardment. These ancient ice deposits preserve chemical fingerprints of early solar system, potentially containing information about primordial disk composition from which all planets formed. Implications ripple outward, encompassing questions about water delivery throughout our solar system, potentially explaining how Earth acquired its oceans, while suggesting similar processes may have operated on other worlds during planetary formation epochs. If our moon can maintain water ice from ancient cometary collisions, analogous mechanisms might have functioned on alternative worlds, potentially explaining water presence on Mars, outer planet moons, and even large asteroid surfaces. Comprehending lunar water conservation mechanisms could supply templates for identifying water resources on worlds we have yet to investigate. Technological obstacles of extracting and utilizing these concealed hemisphere water accumulations are challenging yet surmountable. Robotic systems capable of functioning in extreme thermal environments of permanently shadowed territories are under development, incorporating lessons learned from terrestrial operations in polar climates. Processing techniques required to extract water from lunar regolith and convert it into useful forms like drinking water or rocket fuel are being refined through laboratory experiments and field tests. Economic potential of lunar water extraction extends far beyond simple resource utilization. Water can be separated into hydrogen and oxygen, generating rocket fuel, enabling refueling operations throughout the inner solar system. Rather than transporting all necessary propellant from Earth's deep gravity well, spacecraft could refuel at lunar installations, dramatically reducing cost and complexity of missions to Mars and beyond. This vision of our moon as a cosmic refueling station transforms the hidden hemisphere from scientific curiosity into strategic asset for space exploration. Concealed hemisphere installations could function as staging areas for deep space missions, providing not only fuel but also maintenance facilities, supply depots, and crew rest areas for long-duration interplanetary voyages. The concealed hemisphere's unique electromagnetic environment continues attracting attention from astronomers eager to exploit its natural radio silence. Earth's growing electronic noise pollution makes ground-based radio astronomy increasingly challenging, while satellite proliferation and space debris create additional interference affecting even space-based observations. The concealed hemisphere's position, permanently shielded from terrestrial radio sources, represents one of the quietest electromagnetic environments in the inner solar system. This natural radio sanctuary becomes increasingly valuable as we develop more sensitive astronomical instruments capable of detecting ever fainter signals from distant cosmic sources. Radio telescopes operating from the concealed hemisphere could potentially observe frequencies completely blocked by Earth's ionosphere, opening entirely new universal windows remaining inaccessible to ground-based facilities. Concealed hemisphere radio astronomy's scientific potential extends across multiple research fields. Low-frequency observations could detect signals from cosmic dark ages, providing direct information about the universe's earliest epochs when initial stars and galaxies were forming. Solar system astronomy could benefit from continuous monitoring of planetary magnetospheres and solar wind interactions without interference from Earth's radio environments. The proposed Lunar Crater Radio Telescope represents perhaps the most ambitious astronomical project ever conceived for our moon's surface. This installation would deploy a kilometer-diameter antenna array within a suitable impact crater, creating a natural bowl-shaped reflector focusing radio waves with unprecedented precision. Technical challenges of constructing such installations using robotic systems are substantial, requiring advances in autonomous construction techniques and precision manufacturing in harsh lunar environments. However, scientific returns could justify enormous required investment. A lunar radio telescope of this scale would possess collecting area exceeding all terrestrial radio facilities combined, while operating in environments free from atmospheric interference and electronic noise. Observations possible with such instruments could revolutionize our understanding of cosmic evolution, potentially detecting phenomena remaining completely unknown to current astronomy. Coordination required for international lunar astronomical installations presents both challenges and opportunities for space cooperation. No single nation possesses all resources necessary to construct and operate major concealed hemisphere observatories, making collaborative efforts essential for success. Development of shared lunar infrastructure could serve as a model for future cooperative ventures throughout our solar system. Legal and regulatory frameworks for concealed hemisphere astronomical operations remain largely undeveloped, creating potential complications for international collaboration. Questions about territorial rights, resource utilization, and environmental protection on our moon require careful consideration, ensuring astronomical installations can operate without conflicts over jurisdiction or access rights. Biological implications of concealed hemisphere exploration touch on some of the most profound questions in astrobiology and searching for life beyond Earth. While our moon itself is unlikely harboring indigenous life, materials preserved on its surface may contain information about biological processes operating elsewhere in our solar system during earliest epochs. Organic molecules delivered to our moon by comets and asteroids could preserve chemical signatures of biological activity occurring on other worlds billions of years ago. The concealed hemisphere's limited geological processing means such materials might remain intact longer than similar compounds on more active planets, creating natural archives of ancient biological information. Searching for these potential biosignatures requires sophisticated analytical techniques capable of distinguishing between organic molecules of biological origin and those created through non-biological processes. Laboratory studies of lunar specimens continue pushing boundaries of what's possible in detecting trace organic compounds, while theoretical models explore conditions under which biological molecules might survive harsh interplanetary space environments. Organic material preservation on the concealed hemisphere also carries implications for contamination control during future exploration. Earth-based organisms carried to our moon on spacecraft could potentially survive in protected environments, creating false positive signals in searches for indigenous or ancient biological materials. Developing protocols preventing such contamination while enabling meaningful biological research requires careful balance between scientific objectives and planetary protection requirements. Philosophical dimensions of concealed hemisphere exploration extend beyond scientific discovery into questions about humanity's relationship with the cosmos and our responsibilities as explorers of other worlds. The transformation of our moon's hidden hemisphere from mystery and speculation realm into systematic investigation destination reflects our species' growing capability to extend reach beyond our home planet boundaries. This expansion of human presence into cosmos carries obligations to preserve scientific value of environments we explore, while ensuring our activities don't compromise future discovery opportunities. Our moon serves as humanity's first testing ground for developing ethical frameworks for space exploration, balancing scientific curiosity with environmental stewardship. The concealed hemisphere's cultural significance also evolves as our understanding of this hidden world grows more sophisticated. Ancient civilizations created myths and legends about our moon's mysterious nature, but none could have imagined complex geological processes and resource potential modern science has revealed. The hidden hemisphere represents both culmination of human curiosity and starting point for even grander adventures among stars. Concealed hemisphere exploration's technological legacy extends far beyond lunar science into fields benefiting all humanity. Autonomous systems developed for operating in challenging lunar environments, advance robotics technology with applications in healthcare, manufacturing, and environmental monitoring. Communication systems required for concealed hemisphere missions improve satellite technology and deep space navigation capabilities throughout our solar system. Materials science innovations needed for surviving harsh lunar environments contribute to advances in construction, electronics, and energy storage finding applications in terrestrial industries. These technological spillovers demonstrate how space exploration investments return benefits to society in unexpected ways, driving innovation across multiple sectors while expanding human capabilities. The educational impact of concealed hemisphere exploration continues inspiring new generations of scientists, engineers, and explorers. Students following current missions learn about discovery processes, international cooperation, and technological innovation required for expanding human presence beyond Earth. This inspiration translates into increased interest in STEM fields, contributing to workforce development in areas crucial for future technological advancement. The concealed hemisphere serves as a powerful symbol demonstrating what humanity can achieve through collaborative effort and persistent dedication to expanding knowledge boundaries. As we look toward concealed hemisphere exploration's future, the trajectory appears poised for dramatic acceleration. Multiple space agencies and commercial organizations are developing missions that will expand our presence on the hidden hemisphere, while technological advances continue making previously impossible objectives achievable. Our moon's concealed hemisphere endures with endurance transcending geological epochs, safeguarding within its primordial materials, and collision-marked terrain chronicles of cosmic development occurring during our solar system's tumultuous and violent infancy. Every impact formation narrates brutality on magnitudes overwhelming human comprehension, while every crystalline particle contains data regarding mechanisms functioning under circumstances we can scarcely envision. This evening, as our moon's recognizable countenance ascends in your heavens, recall that immediately beyond that luminous boundary exists a realm of enigmas our species has merely commenced investigating. The identical gravitational choreography generating oceanic tides and stabilizing Earth's axial rotation has maintained for us a natural archive where planetary genesis's most profound mysteries remain etched in stone, anticipating human inquisitiveness to decode their ancient knowledge. The expedition advances with every fresh mission contributing segments to this cosmic chronicle, every revelation exposing both solutions to enduring inquiries and completely novel puzzles challenging our comprehension. Within cosmic chronology's immense scope, our investigation of our moon's hidden hemisphere constitutes merely inaugural chapters of an extensively longer narrative regarding humanity's expanding existence among worlds sharing our galactic region. The concealed hemisphere beckons across space's emptiness, presenting discovery possibilities potentially restructuring our comprehension of how worlds originate and develop, while supplying resources and understanding necessary to transport human civilization beyond solitary planetary constraints. Responding to that summons, we participate in cosmic dialogue, commencing when initial humans gazed upward at nocturnal skies, wondering what mysteries lay concealed within stellar darkness. Within cosmic night's tranquil quietude, as mechanical systems maintain patient surveillance across global lunar observatories, we discover ourselves at revelation thresholds, potentially fundamentally transforming our comprehension of how worlds maintain their most profound secrets. Chang'e expeditions have unlocked passages we never recognized existed, while NASA's orbital guardians maintain their decades-spanning watch, observing and documenting every subtle transformation across this extraterrestrial landscape. Specimens retrieved from South Pole-Aitken basin have exposed volcanic processes persisting far longer than our theoretical frameworks anticipated, indicating thermal mechanisms functioning within lunar interior we're merely beginning understanding. These 2.8 billion-year-old basaltic formations describe a moon maintaining geological activity when we believed it should have been frigid and inactive, challenging fundamental presumptions regarding how compact worlds dissipate internal thermal energy. However, perhaps even more captivating are isotopic fingerprints discovered within these ancient materials. Extreme strontium and neodymium depletion indicates concealed hemisphere mantle experience processing so comprehensive it generated compositions unlike anything discovered elsewhere throughout our solar system. These chemical identifiers indicate events of such enormity they reconstructed lunar internal framework on hemispheric proportions. Creep material discovery on the concealed hemisphere has transmitted reverberations throughout planetary science communities, overturning decades of presumptions regarding lunar development. These potassium, rare earth element, and phosphorus-enriched rocks were considered primarily near-side phenomena, explaining why volcanic processes were substantially more extensive on the hemisphere observable from Earth. Discovering analogous substances on the hidden territory indicates lunar early differentiation was far more intricate and globally distributed than ever conceived. This disclosure compels reconsidering fundamental questions regarding lunar genesis. If heat-generating radioactive elements were more uniformly distributed than surface characteristics indicate, what mechanisms concentrated them so dramatically on the near side? The solution may reside within the colossal South Pole-Aitken collision itself. An occurrence so brutal it potentially triggered hemisphere-scale convection redistributing materials throughout lunar interior. Computer modeling of this ancient impact creates images of devastation on scales challenging our comprehension capabilities. An asteroid hundreds of kilometers across, traveling at cosmic speeds, impacts with energy equivalent to billions of thermonuclear devices. The collision excavates substances from depths potentially reaching lunar mantle, while shockwaves circumnavigate lunar perimeter, converging at antipodal locations with sufficient power fracturing bedrock globally. The subterranean mass anomaly detected beneath the basin by NASA's Grail expedition continues puzzling investigators. This dense material concentration, equivalent to 5 times Hawaii's Big Island mass, may represent fossilized remnants of the impacting asteroid, its metallic core somehow embedded within lunar mantle, like cosmic projectiles frozen temporarily. If this interpretation proves accurate, we possess preserved within our moon unblemished specimens of primordial substances from which all planets originated. The implications transcend lunar science, potentially supplying unprecedented perspectives into early solar system composition and planetary formation mechanisms throughout our galaxy. As we approach our expedition's conclusion into our moon's hidden domain, one reality becomes magnificently evident. The concealed hemisphere has metamorphosed from humanity's greatest celestial enigma into our most promising discovery frontier. From ancient crater documentation preserving our solar system's violent genesis to water ice accumulations potentially fueling our Mars expedition, this alien terrain continues rewriting narratives of how worlds originate and develop. The concealed hemisphere embodies more than scientific opportunity. It represents human potential transforming mysterious into familiar, impossible into achievable, extraterrestrial into comprehensible through meticulous observation, technological innovation, and unwavering determination expanding knowledge boundaries. Tonight, when you observe that recognizable lunar countenance, remember that immediately beyond lies a wonder-filled world awaiting to welcome humanity home among stars. The identical celestial companion inspiring countless generations with its mysterious beauty now offers pathways to futures among distant worlds, advancing humanity's eternal mission to explore, comprehend, and discover our position within cosmos's infinite expanse. The concealed hemisphere summons across space's vacuum, presenting discovery opportunities reshaping our understanding, while providing stepping stones toward humanity's stellar destiny. Answering that call, we honor generations of visionaries who dared imagine seemingly impossible possibilities, while preparing pathways for future explorers carrying human presence ever deeper into cosmic frontiers, awaiting discovery. The hidden hemisphere that remained beyond human perception throughout recorded history has become our gateway to understanding planetary formation, cosmic evolution, and humanity's potential future among stars. Each mission, each specimen, each discovery adds chapters to an epic narrative, beginning with curiosity and extending toward destinations we can barely imagine. Within the concealed hemisphere's ancient materials and preserved landscapes, we glimpse both our origins and our destiny a reminder that humanity's greatest adventures may lie not behind us in terrestrial history, but ahead of us in cosmic frontiers calling across the darkness between worlds.